Okay, hi everyone. Quantum technologies. We're going to pick up from when we stopped last time. So remember, we're at the beginning of the course. We're at the quantum information introduction part. Remember, we're going to do quantum information introduction. That will be today and maybe a little bit at the beginning of next week. Then we will move to our quantum optics intro, light matter interaction, kind of. And then we will start looking into our technologies and so on. Okay, so we're at the quantum information intro. And what we're going to do today is, well, basically we're going to start looking at what is a qubit. We did that last time. Multiple qubits. Okay, we're going to look at operations. We're going to look at all kinds of simple examples. Okay, maybe show like a simple algorithm. And then we're going to talk about the density matrix, which is useful for describing ensembles of qubits. And then we're going to talk a little bit about quantum measurement. Okay. Now, before I actually start, are there any questions with regards to the intro of last week? If you have, please unmute yourself and ask questions if you want clarifications about last week. Okay. If not, we'll continue. Okay. All right. So last time I introduced the qubit for formalities. Remember, a qubit is just a state with some amplitude to be in state 1, state 0, plus some amplitude to be in 1. And of course, the normalization means that alpha squared plus beta squared is 1. And we also said that we can describe this thing on the Bloch sphere. Okay, so we had our Bloch sphere with, this was x, y, and z, and we had some state over here, psi. So this is our state psi on the surface of the sphere. Okay, and this is our state psi, and we could define basically some angle. So we had some angle here phi and angle theta with respect to z, and then you can parameterize alpha and beta. Basically alpha, you could parameterize it as cosine theta over 2, and beta was parameterized as sine theta over 2 e to the I phi. Okay. And so this is our qubit, and we know that if we measure this qubit, then the probability for 0 is just alpha squared, and the probability to get the result 1 is just beta squared. Okay, so this was our qubit. We also know that a measurement can be done in any basis. So here I said, okay, you measure this, you do a projection, really, right? And you get a 0 or a 1. But you can also measure in any basis. Okay, so measurement can be in any basis. Okay? So suppose that psi just equals 0. Okay. This 0 is basically a superposition of the plus and minus state. So 1 over square root of 2 plus minus. Okay, where the plus and minus state Here, maybe if I draw the block sphere over here again. So if this is x, y here, and z, and we said that 0 is the state up here, and 1 is the state over here, then this over here would be plus, and this state on the other side over here would be minus. Okay, and 0 over here is just a superposition of plus and minus. Okay, so let's just define them. Specifically, plus is 1 over square root 2 of 0 plus 1, and minus is 1 over square root 2 of 0 minus 1. Okay? And now if we take this qubit, the state over here, and we measure it, so now we do a measurement, okay, in the plus minus bases, okay, then the probability of getting a plus in this simple case that I wrote is going to be 0.5, and the probability of getting a minus is also going to be 0.5. Okay, and you can choose any basis. So any axis in this sphere can basically be a measurement basis. But what this shows us is that, I'll write it specifically here, is that eigenstates of one basis is a superposition of another basis. Okay. Everyone with me till now? Okay. So maybe I'll ask a quick question. Maybe you can vote on this thing. So the question is, how much information does a measurement of a single qubit give us? Okay, we know that if we have a regular bit transistor, we measure, it gives us 0 or 1, that's 1 bit of information. If we measure a single qubit once, so we get one result, how much information is that? And I'll give you two options. Basically, is it, so for one qubit, okay, is it 1 bit? If it's 1 bit, answer yes. If it's more, then just answer no on the little thingy, on the poll thing. All right, so we have 9 answers, 10 answers. Almost everyone is answered. Okay, everyone is answered, and yeah, we have a majority. So we have 8 voted that we get 1 bit, and 6 people voted that we get more than 1 bit. Okay, the answer is 1 bit. Okay, when you measure a single qubit, you get 1 bit of information about its state, whether it's 0 or 1. Okay. Now, if you repeat this measurement many times and you get statistics, then you can figure out alpha and beta. If I write here, psi in general is alpha 0 plus some beta 1. And as you repeat the measurements over and over again, you can get an estimate of alpha more accurately. Okay, your measurement gives you alpha squared. So every measurement gives you an extra bit, okay, of information. Now the next question is going to be, what happens when we have 2 qubits? In that case, do we get 2 bits of information, or do we get more? Okay. Click on the thing. If we get 2 bits of information, then do yes, and if we get more, then just do no. It's exciting. It's like elections. Who's going to win? Okay, so now we've tilted towards more, right? What's the final result? We have 2 undecided, 8 no, and 5 yes. So we have 8 on the no here, and 5 on the 2 bits. The answer is we only get 2 bits. Okay, now I know that some of your inclination would be, okay, now I have 2 qubits. There's going to be some entanglement. There's going to be something going on. Quantum gives me more. It doesn't. Okay, whenever you measure, a single projective measurement gives you a single number, a 0 or a 1. And that is 1 bit of information. Okay, so out of n qubits, a single projective measurement that gives you, a result for each of those is just a register of n bits. Okay, so for n qubits, the amount of information that you can get is n bits from this single measurement, okay, of all those qubits. Okay, so 1 qubit is 1 bit of information, okay, for a projective measurement. Okay, do you have any questions about that? Clarifications? Okay, great. So what we'll do now is let's define multiple qubits, okay, and let's see entanglement specifically. Okay, so let's talk about multiple qubits. Okay. Or more specifically, entanglement. Okay. So let's suppose that we have 2 qubits now. Qubit 1, going to be psi 1. This will be alpha 1, 0 plus beta 1, 1. Okay. And the second qubit is going to be alpha 2, 0 plus beta 2, 1. Okay, so this is our 2 qubits. And the wave function, the joint wave function for these 2 qubits is just going to be written as some alpha 0, 0. So some amplitude that both qubits are in 0 plus some amplitude that one qubit, that qubit 1 is in 0 and qubit 2 is in 1. And then some amplitude that qubit 1 is in state 1 and qubit 2 is in state 0, plus some amplitude delta that both of them are in the state 1. And of course we have to normalize all this, so 1 over square root of alpha squared plus beta squared plus gamma squared plus delta squared. Okay, so this is the wave function in general that describes the 2 qubits. And if you were to measure this thing, okay, so you measure the 2 qubits. Each qubit gives you an answer, 0 or a 1. And the probability, for example, to get 0, 0 is just going to be alpha squared. Okay.
Can I ask something?
Yes?
We assume that we still measure in the z-axis?
Yes.
For 0 and 1?
Yeah, yeah. For this example, I'm just measuring in the 0, 1, so each qubit gives me 0 or 1. Yeah.
Okay, thank you.
Shay?
Yeah?
If you write it with the normalization, it need to get into the probability of 0, 0, no?
What do you mean? Where?
You normalized the coefficients in the end of the last line.
Yeah. Oh, yeah. Sorry. Let's yeah. So let's define this as n, okay, and then like that. Okay. N is what's inside, so it's squared, so it's fine. Okay. Yes. Okay, and then that will give us, and then this is just going to be, of course, alpha 1 squared times alpha 2 squared of the original qubits. Okay. which is basically just the probability of qubit 1 giving us the result 2 times the probability of qubit 2 giving us the result 0. Okay, and we can write the same line for all the combinations. But what this shows us for this wave function is that basically these two qubits are now, they're independent. This is a separable state. Okay, so this most general state that I wrote is separable. Okay, but if, for example, now, okay, we take, what did I take here? So we're going to set, for example, alpha equals to delta equals to 0. Okay. We did some operation, did something. We'll see later how we do that. But alpha now equals delta. If we do that, now our wave function, psi, okay, is just going to be some beta 0, 1 plus gamma 1, 0 with a normalization now of beta squared plus gamma squared. Okay? And now our two qubits are no longer separable. Okay? They're entangled. And in fact, if we take beta to equal gamma, okay, then we get what is known as a, who knows the name of the state? Bell state. All right, exactly. Okay, so we get a 0, 1 plus 1, 0 over square root of 2. And the Bell state is basically the state that has the strongest correlations for a 2-qubit system. Okay, and this is what you know is entanglement. Now, the Bell state is a very famous state. There are other very useful and famous states, and I want to write two of them down here maybe. So what I'm writing here is a Ghz state, for example. Okay, so I want to talk about different types of entanglement. So a Ghz state is defined as, for 3 qubits, it's defined as 1 over square root of 2, 0, 0, 0, plus 1, 1, 1. Okay, so this is a Ghz state. Maybe I'll give this a title. Hang on. Where's the eraser? It's in the way. Okay. So I'll give this a title, Other Interesting States. Okay, so these are other interesting states. So this is the Ghz state. Okay, it's an entanglement between many qubits. So you have several qubits in 0 plus in 1. Okay. If you extend this to many, many, many qubits, so 0, 0, 0, 0 plus 1, 1, 1, 1, in the quantum information language, this is sometimes referred to as a cat state. A cat state is also referred to sometimes superposition of coherent states. We will learn about those in a few weeks. But this is the Ghz state, and it has an entanglement, okay, between the qubits. They're correlated. You cannot separate this. Now I'm going to write here another state, which is called a W state, which is also an entanglement between 3 qubits. So it's 1 over square root of 3. Can you see the board down here? Yeah? Okay, good.
Yes.
So 1 over square root of 3. And then it's 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0. Okay. Now here, what you have is also another entangled state between 3 qubits. Okay. But for this entanglement example, the Ghz state is different than this W state. Okay, does anyone know how is it different? What's important? What's a distinguishing difference about this?
It's the unit matrix minus the other, maybe?
No, what I'm referring to is how strong the entanglement is between them. Okay? So let me give you an example. So for example, if I have a Ghz state, okay, if I measure qubit number 1, immediately all the other qubits collapse. I know that all the other qubits, I know the state of all the other qubits. I measure number 1, I get a 0, I know that the other 2 qubits are 0. If I measure qubit number 1, and I get 1, I know that the other qubits are 1. And this extends also if I have, 1,000 of them. Okay, so as soon as I measure one of them, I get one information from one of those collection of qubits, I immediately collapse the whole state. Okay. On the other hand, if you look at this W state, if, for example, I measure qubit number 1, what happens? If I get the result 1, then fine, I know the state of the other qubits. The other 2 qubits are 0, I've collapsed. But if I get the result 0, what happens to the other qubits? They're in a Bell state. Exactly. Okay? They're still entanglement. So measurement of one qubit does not necessarily destroy all my entanglement. Okay? So you'd say that the entanglement here is stronger. Okay? In a loose way. Okay? So these are two types of entanglement. Okay? Are there any questions about this so far? No? Okay. So let's continue. Okay, so now we're going to be talking about qubit operations. Qubit operations. Okay? Okay, now a single qubit operation, okay, that's an operation on a single qubit. We can parameterize it as a rotation. Okay, if you remember our block sphere over here, I'll redraw it. So this is our block sphere. Okay. X, Y, and Z. And then we have some psi over here. Then any operation in our single qubit Hilbert space is just a rotation. Okay? So any single qubit operation is a rotation on the block sphere. Okay. So you have like a rotation of 180 degrees. That's like a knot operation. You go from zero to 1, for example. Okay. Now for convenience, so this is just for convenience. We define the Pauli matrices. Okay, so whenever you talk about algorithms, and it's just a language that's developed, and it's very convenient. And sometimes they're marked with X, Y, and Z. And sometimes they're marked with a sigma X, sigma Y, sigma Z. That's the same. Okay, so X defined as sigma X. This will be 0, 1, 1, 0. Okay, Y, which is sigma Y, is just 0, minus I, and 0. And Z, sometimes called sigma Z, is just 1, minus 1 in the diagonal over here. Okay? And these Pauli matrices have commutation relations such that sigma I, sigma j, equals 2I epsilon ijk sigma k. Okay? Now, in an analogy to a spin, because I think most of you are physicists and you've seen operators for spin, so if you just take sigma I, you'll notice that it equals 2 over h bar SI, where SI is just the spin operator that you've seen in quantum mechanics. Okay, so this is just the connection. So a qubit is basically a spin. Okay, a qubit is basically a quantum spin. And you've probably seen this, but I don't know how much emphasis you put on this, but for a spin system, as opposed to continuous systems, you know, like oscillators where you have momentum and position are, you know, non-commuting, they're conjugate observables, and their commutation relation is h bar. Okay? You have the identity. Here, the commutation relation between two Pauli matrices is another Pauli matrix. Okay? Okay. So we said that any operation is a rotation. So now we're going to write this explicitly. Okay? So a rotation around axis A, maybe I'll write it. Rotation around axis A. Okay, so we have some axis A going somewhere here. This will be the A axis. Okay, and a rotation around this axis, RA, is just the operation e to the minus I theta over 2. Theta is the angle of rotation times A. Okay, so this, if you're rotating around the z-axis, this would be A, x, y, and so on. Okay, so for example, let's do a rotation. What do I have here? Rotation around y. So rotation around the y-axis of an angle pi. Okay, so this is the y-axis. So we're rotating in this disk over here by an angle of pi. So we might take us from the state over here minus to the state over here plus or whatever. Okay, and this would just be e to the minus I pi over 2. I'm just plugging it over here. Sigma y. Okay, and if you exponentiate this, you will get the result 0, minus 1, 1, 0, which you will notice equals minus I sigma y. Okay? Ran out of space. We'll move over here.
I think it's just I.
You think just I? It could be just I and I made a minus mistake. Is it? Wait, let me see. So this is sigma y. I sigma y. I minus. No, this is minus 1. I minus minus plus. No, I need the minus here. No? If I just have I sigma y, then I get a plus and then a minus here, right?
Yes, you need the minus.
I need the minus, right? Okay. But I tend to make these mistakes, so yeah, please. Minus signs are ubiquitous. Okay, so let's just write this generally. So generally, okay, R around some axis n with an angle theta, okay, which we wrote is e to the minus I theta over 2 n dot sigma, where sigma is just the vector of the Pauli matrices. Okay, so the three components of the sigma vector is sigma x, sigma y, sigma z. maybe I'll write it here explicitly. So sigma is just sigma x, sigma y, sigma z. Okay? And n is just a unit vector in the direction, in a certain direction. So it would be nx, ny, and nz. Okay? And if we write it this way, then we see that our rotation matrix just comes out to be cosine of theta over 2 times I. This is the identity matrix. Okay? Plus I sine theta over 2 of nx sigma x plus ny sigma y plus nz sigma z. Okay, are we okay till now? So this is simply just a description of a rotation of the Bloch sphere. Okay. Now, when people talk about algorithms, and you open up books, you'll see this immediately if you open up Nielsen and Schwang, then it's very, we define these Pauli operators because they relate to the common gates that are usually used in algorithms when algorithms are written down. Okay. So the common gates, okay, computer scientists, they like to parameterize things into a very small set of operations, okay? So they don't care about how many operations you have in real life. You just want a very small set, and to decompose your algorithm into a set of those basic operations, okay? So the common gates that are used typically in such algorithms is, well, basically we have x, y, and z, the Pauli matrices. Okay, but this is not enough for single qubit control. There's also the Hadamard. So H, this is Hadamard. Okay, and the Hadamard is defined as x plus z divided by 2, which equals 1, 1, 1, minus 1, and 1 over square root of 2. Okay. Now what this Hadamard does, it's a convenient gate to use because basically it takes the state 0 to the state 1 over square root of 2, 0 plus 1. So from 0 it creates a superposition, and from 1 it creates a superposition with the opposite phase. And you can see how it plays out as a rotation on the sphere. So it takes you from 0 to 0 plus 1, or it takes you from 1 to 0 minus 1. Okay, it's the same rotation. Okay, and this is the Hadamard. And you would usually see it in quantum computing algorithms. When you see experiments, you don't typically see a Hadamard operation in experiments. What you will see in experiments is something else called a pi over 2. So I'm going to do like an arrow here, something called a pi over 2. And a pi over 2 is simply a pi over 2 rotation. Now a pi over 2 rotation is very similar to a Hadamard. Okay? You take your state, it's over here, you do a pi over 2 rotation, so it goes from 0 to 0 plus 1. Okay? But note, if I have 0 plus 1, and I do a Hadamard, what happens to the state? What do I end up with? Anyone?
0.
I go back to 0. Okay? The Hadamard, okay? The Hadamard is basically a rotation around this 45-degree tilted axis. Okay? So if you're over here, you will rotate over here, and if you're over here, you rotate over here, like this. Okay? That's the rotation. And here, like that. Okay, so this is what the Hadamard does. A pi over 2 is just a rotation like this. Okay, so if I do 2 pi half rotations, I will go from 0 to 1. Okay, if I do 2 Hadamards, I will go back to 0. Okay, it's a subtle difference, and it really, in a lot of algorithms, doesn't make much difference. And a lot of the time, you can exchange this pi half to a Hadamard with, little to no work. Okay, so when an experimentalist reads a theory paper and he sees h, that's a pi over 2 pulse for the experimentalist, up to some little things. Okay, and vice versa. Okay, another common gate that is used, this is called a T gate. Okay, and it is defined as 1, 0, 0, e to the I pi over 4. Okay, and this T gate is basically a pi over 8 gate. Okay, so what you can see is just, it's a pi over 8 rotation. Okay. And another gate that you will typically see is S, which is basically T squared, which equals 1, 0, 0, and I. Okay, so this is basically the set of, the standard set of single qubit gates. So if you open up like a paper and you see a circuit diagram, then you will see these kind of show up. And the way you draw this, okay, and the way algorithms are drawn in quantum information is a little bit like music, like a staff with music. So each qubit would be represented like a line. So what I'm going to do now is I'm going to show you quickly how it's written, how you would write operations. So basically each line here, so I'm drawing here lines, and each line over here represents a qubit. Okay? So each line is qubit. Each line is a qubit. Okay? And then you just draw your operations here. So you'd have like a X operation. Sometimes people like to put them in boxes like this. And then this qubit would have a Z operation. And then both of them will have Y operations, or whatever. And we're not doing anything with this qubit, and so on. Okay, so these are single qubit operations operating on each qubit. And this is the way it's written. Time goes from left to right. Okay, so this is the first operation that's occurring, then this operation, then these two are occurring simultaneously, and so on and so on. Okay? So this is the way these things are written. Now, except for single qubit operations, what else do we need? Anyone? No, we're all tired? You need a break?
Roll gates.
Multiple.
2 qubit gates. Right, yeah, we need 2 qubit gates. Okay, so so let's learn about 2 qubit gates. Okay, so multi-qubit operations. Okay. And so the two, like I said, with the, computer scientists, they like to decompose things into the simplest thing possible. And the simplest set there is basically universal control over a single qubit plus any 2 qubit gate. That gives us a universal set that we can decompose any algorithm into those basic sets. Now, in a real experimental setup, in a real system, you might have a different set and you would have to figure those things out. But in algorithms, it is very common to decompose your algorithm into these single qubit gates plus an additional 2-qubit gate, and the two most common 2-qubit gates are, one, the C0 gate, okay, which is very familiar also from classical computation. You have a C0, a control knot between 2 bits. And it's defined like this. So this is the matrix that defines it. 0, 0, 0. Wait. And wait, did I write it correct? This is all scrambled up. Sorry. Write it properly. Oh, 0, 1, and there. Is that better? No, this is wrong.
Couldn't
I
be
moved,
in the last row.
yeah,
In the last
I
row.
moved that
Yeah.
one. Yeah. Okay. Now there. Okay. So this is the C0 gate. Okay. The way you draw a C0 is like this. So this is the control qubit with a little circle dot, and here you have the qubit that's being operated on. Okay, so this is your control. So if qubit number 1 here is 0, you do nothing to this one. If this qubit number 1 is 1, you flip the state of that one. And that's exactly what this operation does. You can write this basically, what it does is it maps the state 0, 0 to 0, 0. It will map the state 0, 1 also into 0, 1. It will map the state 1, 0 into 1, 1. And it will map the 0, 1, 1 into 1, 0. Okay, and basically this permutation between these two and these two you can see here in these off-diagonal elements of the matrix. Okay, so basically this flips qubit 2 conditioned on qubit 1. Okay, the second common 2-qubit gate that there is, anyone knows? No, it's a C phase.
CZ.
All the other controlled qubits.
Sorry? There was.
You can do a controlled knot, but you can do also controlled anything else.
You can do controlled anything else, of course. There are many operations that at the end entangle you. Okay? But what I'm just writing explicitly the two most common ones that you will see. Okay? Because when you open an algorithm and you read it, you will a lot of the time see this thing, and a lot commonly you will also see this thing, which is the marking for a C phase. Okay? Other more exotic ones will usually be defined in that paper or where you're reading because they're not as common. Okay? Now a C phase is just 1, 0, 0, 0, 0, 1, 0, 0. Minus 1. Okay? So what a C phase does is it flips the phase of the 1, 1. Okay? So a C phase will take 0, 0 to 0, 0, 1, 0 to 1, 0, 0, 1 to 0, 1, but it will take 1, 1 to minus 1, 1. Okay? Sometimes, by the way, so this is a C naught. This is a C phase. Sometimes the C phase is also written as this, like that, as a control Z. Okay, so sometimes it's called a control Z, sometimes it's called a control phase. What it does is it flips the phase of qubit 2 conditioned on qubit 1. Note that opposed to the C naught, it is the direction doesn't matter. Okay, the direction doesn't matter. And so if you take single qubit operations and you add one of these or any 2-qubit gate that entangles, you get universal control. Now another thing that's important to know is that because this is a 2-qubit gate, this is a 2-qubit gate, these two, they entangle in the same way. So basically you can show that a C naught and the C phase, they're the same thing, up to local operations. Okay? So C phase and C naught are equivalent up to local operations. Okay? Meaning that you can turn C naught into a C phase by just adding around single qubit gates. Okay? All right. Any questions till now? We all following? We're good? All happy? All right. It's 1:20 almost. Okay, so let's take a 10-minute break, and then we'll continue with some simple examples like qubit copying, teleportation, and an algorithm we'll show. Okay, so take a 10-minute break and come back.